Welcome back, AP Calc students. More FRQs of old AP exams. Today we are looking at AP Calc AB year 2018, question number 3. So this question is mostly about derivative graphs with a little bit of potpourri mixed in. And so we are going to be looking quite a bit at the actual graph because that's going to be needed to answer most of the material. Now this is a number 3, which means no calculators allowed. So we're going to use all of our skills and probably some geometry here to figure this out. So here's what it says. The graph of the continuous function g, which happens to be the derivative of function f, is shown above or to the right here. I enlarged the graph. The function g is a piecewise linear from -5 to 3, and the rest of it is the quadratic 2 times the quantity x minus 4, the quantity squared, from 3 to 6. Okay, well let's take a look here and see what that tells us right away. So according to the problem here, we're going from -5 to 2. It's pretty clear that's just a linear function, y equals -3. Then we have this linear function here that's got a positive slope. Then we are once again just a horizontal line at y equals 0. Then we're back at y, a linear function with positive slope, and then y equals 2. And it's at the point 3 where this becomes a quadratic. So it's a piecewise function, meaning there are several pieces. The domain is cut up into pieces with a different function in each piece. But the main part is we've got linear parts, and then at point 3 it turns into a quadratic. And that's what we know so far. But the most important part, which you want to do right away on this one, is it says this is the graph of g, comma, the derivative of f. Well, since that's the derivative of f, this question is nothing more than, can they confuse you with lettering, and are you going to keep the each one of the values straight? So right away, I'm just going to go over to here and say, oh, well, this is the derivative of f. Well, then this is also f prime. Now, they purposely didn't do that to make the question more challenging, but that's what this is. It's a derivative graph. So depending on how good you are at derivative graphs, that's most of the problem is just that. So if we go to A, let's see what they ask. Now, normally on derivative graphs, the challenge or the questions typically have to do with area under a curve, meaning integration, and can you weave those two concepts together? And let's see what they ask here. So it says, if f of 1 is equal to 3, what's the value of f of -5? Well, off to the side here, I'm going to write down what they said this function was, just for reference. So in the question it says g of x, this is from 3 to 6, is equal to 2 times x minus 4 squared. But what I want you to be thinking is, really, what they could have said if they wanted to, is they could have said f prime of x was equal to 2 to the x minus 4, or 2 times the quantity x minus 4, the quantity squared. Those two things are interchangeable. Well, the reason that's important, and if this is f prime, if they want to know f of 1, and we've got the derivative, we want to take advantage of the x values they're asking about and see if we can do part of the equation with an integral and the fundamental theorem, and part of the equation using geometry. So that's always the trick on this type of question. So when they say f of 1 is 3, find the value of f of -5, they're telling you integrate from -5 to 1. Find it with geometry, find it with the fundamental theorem, and let's see what happens. So I'm going to write this 2 different ways. You could say to yourself, well, I'm going to integrate from -5 to 1 of g of x dx. So that would be the area under the curve. It's negative here, but from -5 to 1, because they give us these values. Now, just to be clear here, these two statements are interchangeable. Because g is f prime, we're going from -5 to 1 of f prime of x. Those mean the exact same thing, and for some students it might be better to just make it all f prime, and then every time you see a g, just put f prime. It'll make it easier. But what you should know is that the integral of f prime, or the integral of g, whichever way you want to write it, by the fundamental theorem, means that's going to be f of 1 minus f of negative 5. And that's just the basics of the fundamental theorem. And so they're going to want you to expand that combined with saying, what would that equal using geometry? All we have are rectangles and triangles here. So what I'm going to do is say, I don't care which way you set it up, we're going to use geometry to figure out what this is, area under a curve, and then we're going to set it equal to this and see what we've got. So by geometry, everyone, I'm just going to put geo. By geometry, spell that out. By geometry, I'm just going to pick this apart from left to right. So what it looks like is that from negative 5 to negative 2, I just have this square. That's a 3 by 3 square. So from negative 5 to negative 2, 3 by 3, it looks like it's just 9. So by geometry, I've got 9, and it's actually a negative 9 because it's below the x-axis. Okay, and I think what we'll do here, we'll just go ahead and highlight that. So we just went, okay, well this little chunk right here, that box there is negative 9. Okay, got it. Now we have this little triangle we've got to deal with. And we say 1/2 the base times the height. Well, the base is 1, half of that is a half, and this is 3 units high. So that's going to be minus 3/2. We've got that. There's no area here because the piecewise function is just along the x-axis. There's nothing here. And then it looks like right here we have another right triangle going to 1. 1/2 base times height. We just get 1 times 2 times a half, but it's above the x-axis, so that's a positive 1. So it looks like that's what we get. So again, I'm going to put a positive 1 right there and circle it. And then we had that negative 3/2 here. See if we can fit that in there without being too sloppy. Okay, negative 3/2. And so then we just do a little work here. So what do we wind up with here? So this is going to be negative 1.5. So we get negative 10.5 here. Plus 1. So it looks like we get negative 9.5. All right, so by geometry it's negative 9.5. Now that's equal to, I'm just going to pull this down here, that's equal to f of 1 minus f of negative 5. Okay? And then they told us in the question up here, they said f of 1 is equal to 3. Well, that means negative 9.5 is equal to 3 minus f of negative 5. And the question is wanting to know what f of negative 5 is. So I'm going to add the f of negative 5 over. I'm going to add over the 9/2. And so what I wind up with for a final answer is f of negative 5/2 is equal to 12.5. Okay. And you will see this a lot with derivative graphs. It is, do you know that integrals are area under a curve? Do you also know the fundamental theorem? And they have you combine the two skill sets and analyze what one of the pieces of the fundamental theorem is. So there's part B. Part A. Part B, let's move on. Part B says evaluate from negative 1 to 6 g of x. So you'd say, okay, well, positive 1 to 6 of g of x. And they actually want you to do this. Now, this one you could hesitate, and rightly so, because you might be wondering, well, do they want me, the integral is just area under the curve. If I go from 1 to 6, do they want me to use geometry? And right away I can tell you the answer is no, because geometry is only effective when you've got linear piecewise functions or if you have semicircles. But the fact that this is a quadratic, you do not know how to find the area under a quadratic without calculus. It's not going to be possible. So they must be wanting you to go another direction. It's not geometry this time. And then you go back to the question, you say, oh, that's right, they actually broke this up. They gave me this function. So if they want you to evaluate from 1 to 6, we could figure out from 1 to 3, that's just a square, it's 4. And then we can integrate from 3 to 6, and we actually have the function. I actually wrote it right there. But what I'm going to do, if this, again, is confusing you, you could have rewritten it like this and just said, I don't know, that notation is totally bugging me. That makes sense to me. F prime of x is that quadratic, I'm good. Whichever way works for you. But what we need to do is we need to break this up. And so we're going to break this up into the two chunks here. So what we're going to do is just integrate from 1 to 3 of g of x dx. And we're going to add to it the integral from 3 to 6 of g of x dx. Now g of x is defined differently for each piece. Now for this part we can do geometry, and we're going to, or if you wanted to, it's actually the function of 2. It doesn't matter. In fact, we'll go ahead and we'll be consistent. We'll do it the whole way. So we're going to integrate from 1 to 3 g of x, which is the equation y equals 2 dx, plus the integral from 3 to 6 of g of x. Well, again, g of x is given as 2 times the quantity x minus 4, the quantity squared dx. Okay. Now, again, this is a non-calculator question, so we've got some work to do, but you want to make sure you understand it to this spot right here. You just say, oh, it's the function integrate area under a curve. Okay, I got to break it up because I could do this either way, but this one I have to use my integration skill. So what I'm going to do for this one, I'm going to just come up here to continue, and let's see what we get here. I'm going to integrate 2, and you can integrate 2 to be 2x, and we're going to evaluate that from 3 to 4, or from 1 to 3, and we would get 6 minus 2 is equal to 4. Or you could have went up here and just said, well, the area under the curve from 1 to 3, you could have just looked at that and said, well, that's just 4. Either way, doesn't matter. But the next part of it's a little trickier. We have to integrate from 3 to 6, 2 times x minus 4 squared dx. Well, this part of the integral, there's a couple ways to do it. You could have looked at it and said, well, I'm going to expand that quadratic. And I'm going to go ahead and do that just to show you. You actually don't want to do it that way because it's really messy, but I'm going to show you just for just to make the point why sometimes it might seem easier because it'd be a nice friendly quadratic, but it becomes a little bit of a problem. But this little part here, this 4, I'm going to save that till later. So I know that the answer is going to be 4 plus the rest of this integral. So we'll save that just for space. I'm going to move this over. Well, what if you decided to say, well, it's going to be 4 plus, and I'm going to integrate from 3 to 6, and maybe you just decided to say, well, I'm just going to expand that. I'm going to make that x squared minus 8x plus 16 dx, and then you might have said, well, that's going to be 4 plus, and you go 3 to 6, I'll just distribute that 2 in there, and I get 2x squared minus 16x plus 32 dx. Okay, now this is totally integratable. Add 1 to your exponent, divide by your new exponent, and on this you would say, well, I'm going to get 2x cubed over 3 minus 16x squared over 2 plus 32x, and I'm going to evaluate that from 3 to 6. Okay, now I just want to show you, do you want to put 6 in there and cube it? Do you want to put 6 in here and square it? Do you want to put 6 in here and multiply it by 32? This is kind of heavy on the math, and this is not a calculator question, though you'll have a calculator to do this. This is there's a little hint here that it's like, do they want me to do that much multiplication by hand? There's actually a better way. Now you could proceed and do this, and that's fine if you feel confident. I'm going to show you a little bit easier way with just some u sub would make it a little cleaner. So what I'm going to do is just say, you know what, I'm not going to go that route. I am going to just use some u sub. So I'm going to take that 4 and just leave it here. That 4 is coming from there. I'm going to say, you know what, I'm going to actually make this 3 to 6, and I'm going to do some u sub. In fact, I'll start the u sub up here. I'm going to let u equal x minus 4, and that means my du is going to equal dx. So this would be 2 u squared du. Okay, so the u is squared, and their du is equal to dx, and this is much friendlier. And so you got to be careful because these are x values here, the 3 and the 6. But it seems like it's something a little nicer to do. And in fact, I'm going to switch my x intervals to make this all u based. So I'm going to say, you know what? I'm actually going to make this 4 plus, I'm going to bring the 2 out front, I'm bringing that 2 up front, and I'm going to convert my interval. So I'm going to put 6 into here. 6 minus 4 is 2. I'm going to put 3 into here. 3 minus 4 is -1. And then it's just going to be u squared du. Now, if you don't like that, you can leave these as x-based, and we'll put u back in. I'll do it both ways. All right. So I'm going to continue this way. I'll go down now, and then I'll come back and tweak this one. All right, so we wind up here with 4 plus, add 1 to the exponent, divide by the new exponent, so it's u cubed over 3 times 2. So I get 2 u cubed over 3, and I'm going to evaluate that from -1 to 2. Okay, and so I'm going to get 4 plus, if I put in the 2 here, I get 2 cubed is 8, 8 times 2 is 16, so I'm getting 16/3 minus, put in -1, becomes -1, and that's going to be -2/3. And it looks like I get 18/3 right there, which is actually 6. So I get 4 plus 6, and I would get 10 as my final answer there. Now, if you didn't like that and I lost you there, I'm going to come back here. And you would say, okay, you would get 4 plus. I'm going to move the 2 out front again, and I'm going to leave this as 3 and 6. And I get I'll leave this as u squared du. And you say, oh, I'm going to add 1 to my exponent, divide by my new exponent. So I get 4 plus 2 times u cubed over 3. But these are x values here. X is equal to 3, x is equal to 6. So I have to put u back in. So this becomes 4 plus 2 times the quantity, and u is equal to x minus 4 cubed over 3. And we'll do that from 3 to 6. Okay, and we're going to get the same answer. So for this part of the integral, we get 6 minus 4 is 2, 2 cubed is 8, times 2 is 16, so I get 16/3 minus, put in 3, 3 minus 4 is -1, cubed is -1, so -2/3. 16 plus 2 is 18/3 is 6, I get 4 plus 6 is equal to 10. So in both cases I get 10. Okay? So, A, little geometry fundamental theorem, B, little geometry, but with also just your integration skills. And again, keeping straight that they tried to trip you up here with G being F prime. So there's A and B. All right, let's see if we can fit C on here. I think I'm going to come back up here and see if we can have enough room vertically here to put that in. So here we go for part C. Part C says in the question, for -5 is less than x is less than 6, so for the entire distance here, on what open intervals, if any, is the graph of the function both increasing and concave up? Okay, so the question is, what intervals is it increasing, and when is it concave up? Well, when you hear increasing, you should say, oh, well, that's when the derivative is positive. So it's increasing when f prime is greater than 0, and when is it concave up? Well, there's two ways to look at that. You could say, well, it's concave up when the second derivative is greater than 0, or you could say when f prime is increasing. Those are the two ways to do it. Okay, so this question right here, the top here, is asking about f, the original function. When is it increasing? When it's greater than 0. When is it concave up? When its second derivative is positive, or when its first derivative is increasing. So let's look at this part and figure out if we can say, all right, where is f prime greater than 0 or positive? Well, this is f prime. Remember, it's g, but it's f prime. So where is this greater than 0? Well, the graph's a little bit messy here because all the marker spots on it. But it winds up becoming positive after 0. So it's increasing, or it's a positive from 0 all the way here to 4, and it kisses the x-axis here, and then it increases. So we'll just put this, I think we'll put this just in interval notation here. So where is the first derivative positive? Well, it's positive from 0 to 4, and then we're kissing the x-axis right there. So I'm going to put a comma, and I'm going to say from 4 to 6. Okay? There would be where it is where the first derivative is positive, so that's where it's increasing. But then this next question here, so let's go to here, where is this happening? Well, where's the second derivative greater than 0? Well, if you wanted to look at the second derivative, you'd have to sketch the second derivative using kind of the handcuff method and sketching it. You would make this red, and we would make a blue second derivative. That's a little cumbersome on this one. It's doable, but it's a little tricky. It's much easier to just memorize this more advanced rule, which is the original is concave up when its first derivative is increasing. So then you could say, well, where's the first derivative increasing? Well, it's only increasing in a couple spots here. We're increasing over here. I'm only going to look at where I have to be looking at where the derivative was positive, so I actually don't even care about this because it didn't qualify by the first part. But where is the first derivative, where's the first derivative increasing? I would look at it. I would say, well, it looks like it's increasing from 0 to 1, and it looks like it's increasing from 4 to 6. Now, just to be thorough here, I guess I'll go ahead and put this on here. I'm going to make a little line right here to separate these. So where's the second derivative positive, or where's the first derivative increasing? It looks like it's going from -2 to -1. It's increasing. It's also increasing from 0 to 1. Then it's constant, and then it's decreasing. And then also from 4 to 6. So those are the 3 times that it's increasing. Now in order, it says where is it doing both? So where is it both increasing and concave up? So where do these things both happen? Well, they definitely both have 4 to 6. That's happening. And it looks like this never occurs over here, so it's definitely not this one. And then between 0 and 4 and 0 and 1, they have 0 to 1 in common. So it would actually be this one as well. And so where is it both increasing and concave up? I would just put it in interval notation, and I would say f is both increasing and concave up on the intervals 0 to 1 and 4 to 6. Because the first derivative is positive and increasing. And there you have it. That is C. Now I think we have a little room here to squeeze D in. And question D says, find the x-coordinate of each point of inflection of the graph of f and give a reason for your answer. Well, in order to do this one, I'm actually going to do a little bit of notes and then erase them and then just do this question. So this is a really good idea to have just to review or have in your notes, and that is this function. So if I were to give you, that's my x-axis, and I were to give you a classic, just a cubic function. Cubic behavior, and that's going to be in black. And this is review from curve sketch or from derivative sketching earlier in the year. And with this we would say sketch the first derivative, and we would handcuff it. And we'd say, well, we always handcuff the peaks and the valleys. And we would say, well, we handcuff the peaks and the valleys because the derivative is 0 at peaks and valleys and flat spots. And so we would say it's got to go through here. Those are the x-intercepts of the derivative. And then you ask yourself, what's the original function doing? It's increasing, therefore its derivative must be positive. And you can draw that part. What's the original function doing between the handcuffs? It's decreasing, therefore its derivative must be negative. But it's got to get back to 0. What's the original function doing from the second handcuff to infinity? It's increasing, therefore the graph of its derivative must be positive, and that would be f prime. Then if you want to sketch the second derivative, you treat the first derivative like an original and you handcuff its peaks and valleys, and I would come to here, and I'd say what is red doing from negative infinity to its minimum? it's decreasing, therefore the graph of its derivative must be negative. What's the red function doing from the minimum to infinity? It's increasing, therefore the graph of its derivative must be positive, and there would be f prime. Now, a little check is that if you did the second derivative correctly, it will correspond to an inflection point on the original function, and sure enough it does. Now this little question, this little example here, is actually going to reinforce a concept from part C. Where is the original function concave up? It had said, where is it increasing and concave up? So let's look at this function here. Look at the black. Where is the black increasing and concave up? Well, it's increasing here to the first handcuff, and it's increasing from the second handcuff to infinity. And where is it concave up? Well, it's only concave up from this inflection point to infinity. So where is it both increasing and concave up? Where the first derivative was both positive and increasing. So look at red. Where is red both positive and increasing? The only spot where it's positive is at the ends, but positive and increasing is only the second one. So if you'll notice, positive and increasing is right here, corresponds on the black to increasing and concave up. So this is a great little graph to always have, and I recommend having it available, and it's really helpful. Now with this, I'm going to erase this and show a second one that helps explain part D here. So let me get rid of this and then show another version of the original function that will help. So what if we had this? There's my x-axis. What would happen if we had, here's my original function, we have a peak, and on the way back down we have a flat spot before it changes direction. Okay? So now it's time to sketch the derivative. So let's be thorough here and make this f prime, or sorry, just f. All right, let's sketch the derivative. So I'm going to go to red, and I'm going to handcuff. So I handcuff peaks, valleys, and flat spots. That's where my derivative is 0. So I have a little peak right here, and I come down and I handcuff it. I have a valley bottom right here, and I handcuff it. But I also have a flat spot right there, and I handcuff it. So this has 3 times where the derivative is 0. So let's see what we do here. The original function is increasing, therefore the graph of its derivative must be positive. The graph of the original function is decreasing, therefore the graph of the derivative must be negative. The graph of the original function continues to decrease. Well, what just happened right here? Instead of handcuffing it there, it just kisses and keeps coming back down to 0. So I was the original function was increasing, therefore the graph of the derivative was positive, but the original function was decreasing all the way from the first handcuff to the second with a brief pause in the middle. Therefore the graph of its derivative was negative the whole time with a kiss right there before it came back to the third handcuff. The original function is increasing, therefore the graph of the derivative must be positive. And I'll call that f prime. Okay, so what I want you guys to notice is, look where the kiss is occurring. So when your first derivative is kissing, it corresponds to a flat spot or an inflection point. So now we will switch to our second derivative. So in blue, I'm going to handcuff the flat spots. So my valley bottom here, and my valley bottom here. And this peak is weird, it handcuffs itself right there. So let's look at what the red function is doing. Red is decreasing all the way to here, therefore the graph of its derivative must be negative. From here to here, the red function is increasing, therefore the graph must be positive. The red function is decreasing from here to here, or from here to here it's decreasing, therefore the graph of its derivative must be negative. And then from this handcuff on, it's increasing, and so the graph is going to be positive, and there would be the second derivative. And what you could even see is that it's possible that the original function was 5th degree, perhaps. Its derivative would be 4th degree. We have a nice W, and its derivative would be cubic, which is what we have there. But the point I want you to focus on this one, really important, is what do derivative kisses generate in the original function? Well, wherever the derivative was kissing, actually, what we're going to do before I polish that off is, again, your x-intercepts of your second derivative will always correspond, if you do it right, will always correspond to inflection points or where concavity changes. So I have concavity changes right there, and even this one right here. So x-intercepts of my second derivative correspond to inflection points. I have 3 of them. I'm concave down, concave up, concave down, concave up. But what also happens is I want you to see how the kiss of the first derivative corresponded to an inflection point. That's a cool little shortcut that you want to keep remembering. Kisses of the first derivative correspond to flat spots or inflection points on the original function. Really important. And you're going to see why, because that little shortcut helps you a lot on this next question. So now for part D, here's what they say. Part D says, looking at the graph here, part D says, okay, find the x-coordinate of each point of inflection of f, give a reason for your answer. Well, just for the sake of space here and clarity, that original graph there that's kind of drawn here, I'm going to put this right here so we have a little something to look at. So your question is, do you have any places where you increase, kiss the x-axis, or if you're negative, kiss the x-axis and then continue to stay negative, or anywhere where you're positive, kiss the x-axis and then continue to go positive? Well, if you look at this graph, it kind of jumps out at you now. And again, g is equal to f prime. If you look at this, we have this kiss right here, which tells us, reading left to right, what was the original function doing? Well, it's decreasing, decreasing, constant. It's increasing all the way to here, and then it kisses and continues to increase. So it jumps out at you right here. There's the it's when x is equal to 4. So for part D, it says, find the x-coordinate for each point of inflection of the graph, and it's obviously right here as well. Okay, but the only spot where that's going to happen is, you could say, well, it's occurring at x is equal to 4. And your explanation is going to be because f prime of x goes from decreasing to increasing. And that's just a mathy way of saying kissing, or the other way around. Whenever you have a kiss, your derivative is going from decreasing to increasing, or if it was from below, increasing to decreasing. So that's how you say kissing mathematically here. So at x is equals to 4 because the derivative goes from decreasing to increasing. All right. So there it is, 2018 number 3, a potpourri question, and really pretty heavy on derivative graphs. So thanks for watching.